Away we go. This is a video for my 30S Pre-Cal students. For people who want to see these examples again or they missed the class, we have a heavy snowfall last night, so there's a bunch of people who didn't make it in. So for anybody watching this for the first time, we did hand out a couple of new booklets today. The first booklet has a big A on it, but it says Chapter 6, Rational Expressions and Equations. So if you're trying to do this lesson, you don't have the book, you might want to just jot things down on loose leaf, or you could print this out from the blog. And we're going to start in lesson 6.1. And as you can see, lesson 6.1 is about rational expressions. Rational meaning that you have a numerator and a denominator. A rational expression is an algebraic expression that can be written as a fraction, such as 2/3, or 4x minus 5 over 2xy, or 5x squared over 3x squared plus 4x minus 7. Equivalent rational expression is a rational expression that may be expressed in many different forms. For example, 2/3 and 4/6 are exactly the same fraction. So is 200 3/100ths, or 8/12ths. No, wait a minute. 8/12ths, etc., etc. You could make an infinite number of these. And algebra works the same way. X minus 5 over x is the exact same expression as 2x minus 10 over 2x. Or it's the exact same expression as x over x plus 5. Right? See the logic on that? Because pick a number for x. Suppose x was 10. Then this would be 5 over 10, which is a half. This would be, oh, wait a minute. It's not the same, is it? Is this the same as that? No. So it's not a matter of adding the same number to top and bottom. You have to multiply or divide the same number from the top and bottom. So another one that would work, so put an X through that if you wrote it down. Another one that would work would be something like, oh, I don't know, 3x. Let's just stick to small numbers. 3x minus 15 over 3x. Okay, let me give you another what if. So adding or subtracting does not make the same rational expression. We just proved it. But what if we squared it? So I'll put it in red because I don't know yet. Is x squared minus 10x plus 25 over x squared an equivalent expression to the original one? Again, pick a number for x. Let's say x was 1. This would be negative 4. If I put a 1 in here, do I get negative 4? Definitely not. So the rule is, a rational expression may be expressed in many different forms, but all of these forms, I guess I can get off of red, all of these forms are simplifiable to a simplest form. So let's kind of look at our three examples here, right? For 2/3, all of these things would simplify down to 2/3. And then that's 2/3 is as simple as it can get. You can't make it any simpler than that unless you wanted to, or it wouldn't be any simpler. You could say, well, you could divide top and bottom by 2 and have 1 over 1.5. But that's not really simpler because you've introduced a decimal. The simplest form would mean integer over integer, as simple as it can be. And algebra is the same way. If I started with 2x minus 10 over 2x, I could factor a 2 out of the top and a 2 out of the bottom, and then divide those 2's. And notice that gives me x minus 5 over x. All of the forms that we call equivalent simplify to some simplest form of the same thing. Please note that when you're looking at 2x minus 10 over 2x, okay, we just proved to you, hopefully, that this is equal to x minus 5 over x. The most common mistake people make when they're doing algebra that's in fractional or rational form is they say to themselves, oh, hey, hang on, 2x divided by 2x is 1, so this answer is just negative 10. No, it isn't. First thing I'll say is, well, hang on a sec. When you divide something by itself, does it make 0? And they'll say, oh, you're right. 2x divided by 2x is 1, so it's negative 9. No, it's not that either. Because logically speaking, if you have this kind of a divide, you're implying a bracket, right? This is one term to you, really. This is one binomial, and it has to be divided in both terms by the 2x. You could, if you wanted to, write it like this. That's okay. But of course, it's not really any simpler. It'd be 1 minus 10 over 2x, which is 1 minus 5 over 2x. And I don't know that mathematically I consider that simpler. Do you? Still good. Again, let's pick our favorite number. What's our favorite number? 1. 1 minus 5 over 1, that's negative 4. 1 minus 5 over, oh, hang on a sec. Did that work? Oh, sorry. I made a mistake. That's better. 1 minus 5 over 1 is negative 4. It is right. It is true. But is it simpler? See, to a mathematician, this isn't really simpler because it's two different things. It's two different numbers. Whereas if I take a common denominator to that and I end up, well, back here, if I have 1 minus 5 over x and I say, I want this as a common denominator, so I'll times it by x over x. Now I'm back to here. That, I think, is what a mathematician would consider the simplest form. Certainly simpler than either of these two guys, and simpler than this. Okay? So there's equivalent expressions. The next kind of concept we need to talk about is restrictions, also known as non-permissible values. I'll usually call these NPVs, non-permissible values. And okay, what's 0 divided by 5? Well, last time I checked, that's 0. What's 5 divided by 0? Aha, there is no such number. It's called undefined. If we've never had the conversation as to why that's true, once again, let's use some scrap paper here. And let me show you what I was thinking here. Suppose I had 0, oops, come back. Suppose I had 0 times 3 is 0. That's a true statement, isn't it? Well, if that's true, then I should be able to make a division statement out of this, shouldn't I? Kind of like if I have 2 times 3 is equal to 6, I can make 2 division statements out of that same fact. I can say that 6 divided by 3 is 2, and 6 divided by 2 is 3. Can I do that here? Well, the answer to that is kind of no, because think about it this way. Multiplication is repeated adding, right? What is 2 groups of 3? Well, 3 plus 3 is 6. And then when I undo that, when I make the opposite statement, the division, well, the opposite of repeated adding, is repeated subtracting. So when I ask you what 6 divided by 3 is, and I'm thinking about division as a repeated takeaway, I'm asking you how many 3's do you take away from 6 to make it to 2? So start with 6, take away 3, now I've got 3. Take away 3 more, oh, there we go. It took me 2 to get rid of this 6 by taking away 3's. What if I was getting rid of this 6 and I was taking away 2's? Well, then it would take me 3 steps, right? I'd start with 6, I take away 2, I got 4, I take away 2, I got 2, and then 0. So it took me 1, 2, 3 steps. Notice that's not an equation, or that's not a question I can kind of do this way. I can say, all right, well, 0 divided by 3 is 0. That's okay, that's true. How many 3's do I take away from 0 to get to 0? None. But notice the question isn't really askable this way. How many zeros do I take away from 3 to get to 0? Well, if I take 3 and take away 0, I still got 3. Take away 0, I still got 3. Take away 0, I still got 3. See the problem? I'm never going to get to 0. Every once in a while, you'll see a teacher who tells their students that, oh, the answer to this is infinity. That's actually not true. Logically speaking, I could infinitely take 0 away from 3. I'm still not getting to 0. Okay? When we start our calculus course next semester, you'll see that this kind of thinking here, that something divided by 0 is infinity, is a good way to think when you're doing calculus, but only under specific circumstances. When I'm just dealing with integers, numbers, I can't divide by 0. Rational numbers, irrational numbers, real numbers. I can't divide by 0. So that's kind of the unbreakable rule in math. In math, you can't divide by 0. So 0 divided by m is 0, no problem. But m divided by 0, undefined. 0 divided by x minus 3, no problem. It's 0. Wait a minute. It's 0 if x isn't 3. You mean you can't even divide 0 by 0? Nope. Because again, why can't I divide 0 by 0? Well, because again, I can't flip this statement into a divide and get a specific answer. Because yes, 0 groups of 0 is 0. I agree with that. But let's try to turn that into a divide. 0 divided by 0. How many zeros do I take away from 0 to get to 0? Well, you could say, well, 0. But couldn't I also say 4 and 7 and 12 and 3,716? There's no defined answer to this question. So it is undefined under all circumstances when you try to divide by 0. So undefined. And this one here, this is only defined as long as x isn't 3. When working with rational expressions, no factor in the denominator can equal 0, since the value of an expression would then be undefined. Any value that gives this result is called a non-permissible value, or NPV for short. Note, the non-permissible value should always be stated with the answer. The non-permissible value must be found before simplifying. All right, so what are the non-permissible values in these expressions? Well, in example 1, x can't be 0 and y can't be 0. Because if either of those two numbers are 0, you'd have 6 divided by 0. What about in b? Is 0 okay? Yeah, it is, because if k is 0, I just have negative 5 on the bottom. I can divide any number you want by negative 5. But think about it this way. Think, what makes k minus 5 equal to 0? So we've solved stuff like this when we've done our factoring. So 2k would equal 5, k would equal 5 halves. Therefore, the non-permissible value is 5 halves. Or, another way to say this is, k cannot equal 5 halves. You have to pay attention to language when you're talking about this stuff. If I asked you the question, what values would be non-permissible for A? And you answered by saying x equals 0 and y equals 0. I'd say, yeah, full marks. You're right. Those values would be non-permissible. But I kind of like this answer better. I like saying that this thing only exists if x and y aren't 0. Or, better yet, the non-permissible values are that x would be 0 and y would be 0. So if you're going to say that they equal the things that make you divide by 0, make sure you put the NPV in your statement so that I know that you understand that those are the forbidden numbers. Those are the numbers that you can't have for your variable. Okay? All right, look at C. What are my NPVs for this one? Or, say it the other way, what can B not equal? B cannot equal 0 or -6. Do you see why that is? If this B was -6, I'd have -6 times 0, which is 0. And then I can't divide 0 into 5. Ah, what do we do with D? Again, maybe before I move on to D, or I could say my non-permissible value are 0 and -6. Notice when there's only one variable, I don't have to say what the variables are like I did in A, because there's two variables, so I had to make sure that I listed them both. I'm happy with this as an answer for C. All right, now let's move on to D. What do you think? What would make that 0? This should feel familiar. We just did this. My non-permissible values happen, that's a colon, sorry, when a squared plus 5a minus 6 equals 0. Ah, flashbacks from last unit, right? This is plus 6 minus 1. So my non-permissible values are when a is -6 or a is 1. Or again, another way you could say this is the domain of this expression. What's the domain of this expression anywhere that it exists? Well, my domain would be x cannot equal -6 and 1, but it could be any other real number you like. So why can't a be 1? Well, because try plugging it in. You get 1 plus 5 minus 6, which is 0. And then you'd be dividing by 0. And that's the unbreakable rule of math. We can't divide by 0. All right, so there's example 1. And then there's some practice for you on this page here. So this is going to be like a homework page. So then skip to the next part, and let's do some simplifying. To simplify a rational expression, it is usually necessary to factor the numerator, the denominator, or both. This will usually give multiple factors which can then be reduced, and reduced basically means divided out. A rational expression in its simplest form or lowest terms when the numerator and denominator have no common factors other than 1. So for example 2, simplify the following rational expression. So number 1, factor the numerator and denominator. Well, the numerator is kind of already factored. It's 2 times x. But the denominator I can factor out an x, leaving me x plus 1. Simplify or cancel, and it's canceling, I like that they put it in quotation marks. I'm not a fan of sometimes the word cancel. Simplify or cancel actually in this case means divide, right? So in this case, x divides by x, and x divided by x is 1. So this simplifies down to 2 over x plus 1. But I should state my non-permissible values. My non-permissible values here are x can't equal 0 and x can't equal -1. So basically what I'm telling you is that for every number in the universe except for 0 and -1, this thing is equal to this thing. Pick any number you like and plug it in for x, and these two expressions will give you the exact same result. But there's 2 numbers where it won't, and that's 0 and -1, because in both cases it's undefined. All right, let's look at example 3. Yep, what, did I goof something up? Yeah, but over here, 0 plus 0 is 0. So the question is, why can't x be 0? When I put a 0 in here, I get 1. Life's good. But like I said, these two expressions have to be equivalent. And if I plug 0 into this, I get 2. If I plug 0 into this, I get an undefinable statement. So they're not equivalent when x is 0. This one doesn't even exist when x is 0, right? Because I'd have 0 divided by 0, which is not a defined number. As it said in the last page, let's back up a page for a sec. Sorry, back up 2 pages. The non-permissible values must be found before simplifying. So when I was looking at that one there, it's like, well, wait a minute, why can't I have a 0 here? Because this statement used to be this statement. And back before I simplified it, x couldn't be 0. Okay. All right, let's move on to some quadratics. Factor the numerator and denominator. Okay, what 2 numbers times to make negative 10 add to make 3? Plus 5 and minus 2. What 2 numbers times to make 15 and add to make 8? Plus 5 and plus 3. Okay, so this simplifies to x minus 2 over x plus 3. Because x plus 5 divided by x plus 5 is 1. So again, if you like the word cancel, you can say they cancel. But my non-permissible values are x can't be negative 3 or negative 5. And again, it's like, well, negative 5 is not a problem in this expression. You're right, it's not. But in this expression, it would make the denominator 0. And I can't say they're equivalent if I can find a number where I don't get the same answer when I plug it in for both things. So this thing here, this big expression that we started with, is equivalent to this as long as I avoid those numbers. So for every other number in the universe, those 2 expressions are identical except for those 2. Non-permissible values. Okay? Just to show you something kind of, this isn't in the notes. I'm just going to go off of I'm going to go to Desmos here. But how about I do this? Suppose I take y equals, let's use the example we just had here, x squared plus 3x minus 10. Now we know that that's a parabola, right? But what if I said that it was divided by, and let's say x plus 5. Okay, so if we could simplify that, because we already know that this factor is in here. We can factor the top and get x plus 5 times x minus 2 divided by x plus 5, right? And then this divided by that is 1. So if I were to graph this thing using Desmos, I should get this line. Let's see if that's true. So I'm gonna just do some graphing here. Okay, hold on. Oops, there we go. Oh, go away. Desmos, and I'm just gonna move the Desmos over to here. There we go. Okay, so I'm gonna graph y equals x squared, and it was it minus 3x or plus 3x? It was plus 3x, right? Yeah, plus 3x minus 10. And we got exactly what we expected, a parabola. But if this thing had a denominator, let's put a denominator on it, divided by x plus 5, hey, like I thought, it's linear. It's the exact same line as y, I don't know why this keeps popping up, equals x minus 3. Oh, wait a minute, minus 3? 2, that's better, x minus 2. It's the same line, see, it's red, it's blue, it's red, it's blue. So it's the same line exactly, right? If I were to trace points along this line, let's see, there we go, 5, 3 is a point. There we go, right? And negative 5, oh, come on, you. There we go, -5, -7 is a point. Okay, check this out though. If I go back to this one, which looks exactly identical, can you see that? There's a hole in it. If I was actually going to graph this thing on paper, because it was my homework or something, I would actually graph this thing. I'd say, well, I know this thing is basically this line. Whoa, hang on. I know this thing is basically this line, right? Y equals x minus 2, which means it goes through -2, and it has a slope of 1, so it goes up 1 over 1, up 1 over 1, up 1 over 1. But as I'm graphing it, badly, as you can see, as I'm graphing it, I put a hole in it. Because when x is -5, this thing doesn't exist. Okay? So canceling something doesn't remove its non-permissible value. Hopefully that little graph proved that to you. And I actually had a chance to have a conference once with the guys, one of the guys who programs Desmos, and I said, why don't you actually just like make that circle, like make open dots nice and big so people can see them. They don't have to trace to find them. And they said, oh, what the teachers we had for consultants when we were doing the programming, they didn't want to just have that so easy for kids to just see. They wanted kids to be able to figure it out. So they didn't want to kind of spoil the fun on questions like this. So that's why they do it that way. Anyway, let's go back to the notes. That was a fun little diversion. Got to graph some stuff. All right, simplify the following rational expressions. So for A, well, let's see. First of all, what's 18 divided by 10? Well, I don't want a decimal, but I want the simplest fraction I can get. 18 and 10 have a common factor of 2, so I'm going to have a 9 on the top and a 5 on the bottom. Okay, what about d to the 5 over d to the 7? Let's just do this on the side of scrap work. D to the 5, that's a d, divided by d to the 7. Isn't that d to the 5 minus 7, which is d to the -2? But I don't really want negative powers, because to me a negative power is not simplified. So I'm going to have the d squared down here. Is everybody cool with that? D to the -2 is 1 over d squared. Another way you could think about this, if negative powers aren't your friend, they better be your friend pretty soon, because we see lots and lots of negative powers when we do calculus next semester. But if you need another way to think about this, you could also think, you don't have to write this down if you don't want to, d to the 5 over d to the 7 is literally d times d times d times d times d, there's 5 of them, over 1, 2, 3, 4, 5, 6, 7 of them. So that one divided by that one's 1, that one divided by that one's 1, 1, 1, 1, and what have I got left? 1 over d squared, right? Quick refresher on how powers work. Okay, back to the question. I have c to the 4 divided by c cubed, right? Because again, that's like saying c to the 4 over c to the 1 is like saying c to the 4 minus 1, which is c cubed. I'm kind of intruding on my next question there. All right, what do I do with b? Okay, don't write this down. Why is that wrong? Right, because see the difference? It's like, but you kind of did that here. You just canceled 5 of these and left behind 2. Why can't I do that? Because see the inherent difference between the first one and the second one here, between A and B, is that this is an add. This is a binomial. I have to start by thinking factor. Factor out 3a. And then you get a plus 3. No, you don't. Sorry. You get 2a plus 3. And then in the bottom, factor out 3a from the bottom as well. 3a comes out of here and leaves behind 4a. Those divide. 3a divided by 3a. You can cancel factors, you cannot cancel terms, right? These are the two terms that make up a binomial. You can't just cancel one of them. So this is 2a plus 3 over 4a. Can I cancel those a's? No. Can I cancel the 2 and with the 4 and leave that as a plus 3 over 2a? No, it doesn't work that way. You can't cancel terms or parts of terms. You can only cancel factors. Now, as you get kind of more comfortable with this, you probably won't do this step. You probably won't write it out. You'll just kind of do that mentally. You'll go, oh yeah, I can take 3a out of those two things and 3a out of that thing. What's left? But until you're really good at not making mistakes, I really recommend that you take a second and show the factoring. Let's try another one. Okay, what can I do at the top? Well, I see a common factor of 5. What can I do at the bottom? It's a trinomial that I can factor. What two numbers times to make 15 and add to make negative 8? Negative 3 and negative 5. Now that we are in factored form, I can divide factors by themselves. You know, another way to think about this is a number times a number, all divided by a number times a number. Remember that BEDMAS and BEMDAS are the same thing? It doesn't matter whether you divide or multiply in terms of order you do a calculation. So I can do this divide before that multiply and leave behind 5 over y minus 5. And then I just know it. I can sense it. I've been doing this a long time. I know what's going to happen on the next test. Somebody's going to do all that beautiful work. They're going to get right to there, and then they're going to cancel the 5s. Can't cancel those 5s. Right? Again, think, nothing you do in algebra should break arithmetic rules. If you had 5 over 2, can you cancel anything? Because 2 is 7 minus 5. Can I cancel those 5s? Say that that's 1/7? Oh, sorry. When I cancel it, it leaves a 1. It's 1/6. No. No, 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 no. This is the answer. That's as simple as that thing gets. And, hang on a sec, this thing only equals that thing as long as I avoid 2 numbers. What are the numbers I got to avoid? Y cannot equal 3 or 5. You know what? I kind of forgot to do that on A and B. Let's go back to A and B real quick. Simplified. So this thing simplifies to that as long as I avoid what numbers? Well, D can't be 0 and C can't be 0 because there's no add or subtract, so it's just 0. Here, same thing. This expression simplifies to that expression as long as I avoid A being 0. All right, let's move on to D. What do I do with D? I'd like to make it as simple as I can, so I'm going to use this trick here. I'm going to factor the top, f minus 4 times f minus 4. If you said f minus 4 squared, that's fine. That's the same thing. Now, it kind of looks like I have an f. I don't really have an f minus 4. If I factor that as a difference of squares, I get 4 minus f, 4 minus f. 4 minus f is not the same as f minus 4. So you know what I'm going to do is I'm actually going to factor a negative 1 out of the bottom. Now, look what I can do. Now I have f minus 4 on the top times itself. And on the bottom I have a negative 1. And then I have f plus 4, f minus 4, right? Because remember, this thing here is a difference of squares, right? Now I can divide this factor by that factor. And I get f minus 4 over. Now, I kind of don't want that negative 1 there. What do you want to do with that negative 1? Well, you can do a couple of things. You could put it back through, you could multiply that back through and say that it's negative 4 minus 4. That's a good answer. Or, you know what else you could do? You could say it's f minus 4 over f plus 4 but the entire fraction's a negative. Put the negative in front of the whole fraction. This was something you were supposed to learn in grade 9, that these three numbers here are all negative 0.5, right? Doesn't matter where a negative is on a fraction, really. Numerator, denominator. Just make sure you understand that if you do multiply it back into the brackets, it belongs to both. You have to distribute it to both terms. So put a star by this one. That's a very common trick when you're trying to simplify. You look at it and go, oh, the top almost cancels something from the bottom, but if I were to just factor out a negative, then definitely I can do some canceling, right? I mean, logically speaking, this is definitely a simpler looking expression than this, right? If this was a formula you had to plug numbers into, wouldn't you rather work with this one? It's less stuff. Oh, but don't forget, this thing only equals that thing if I avoid what numbers? What can f not be? Think about it. What can f not be? Go to the factored form. Go to this step here. F can't be plus or minus 4, right? Because if f was 4, I'd have 16 minus 16. If f was negative 4, I'd have 16 minus 16. So this expression makes this expression, or this one, whichever one you like better, as long as we stay away from plus or minus 4. All right. Next. More factoring. All right, the top factors to, oh, I think we got a perfect square trinomial there. 2x minus 3 squared. I'll leave this one as a squared. And this one is 2x plus 3, 2x minus 3. All right. Advanced canceling technique here. Some teachers don't like this, but I don't mind it. I think this totally makes sense to me. See if this makes sense to you. Are you okay with that? People are nodding. People are nodding their head. They're seeing what I did there. Would it help if you saw me do it with just ordinary numbers? Right? If I had just, or just, how about simple letters? If I had a squared over a times b, would it be cool if I just went, nah? Because a squared divided by a is a. Does that make sense to you? So there you go. So there we go. My final answer for this one is 2x minus 3 over 2x plus 3. Ooh, could I make that a 1 if I factored a negative out of the top like I did on the last question? And the answer is no, because if you factored a negative 1 out of the top, sure, you'd get a plus 3, but you'd also get a minus 2x. So it wouldn't be the same binomial. So no, that's as simple as that one gets. That's my answer, as long as I avoid what? Plus or minus 3 halves. Correct. Okay. Let's try F now. Ooh, decompositional factoring. What two numbers? 2 times negative 15 is negative 30. I might want to use scrap paper here. What two numbers times to make negative 30, but they're 1 apart? They make negative 1 when you add them. Negative 6 and positive 5. So I think I'm going to do this one. I like, some people don't show this stuff. I like showing this stuff. To me, it just makes more sense to kind of see this. And you know what? I have an advantage over you. Of course, I know where the skills got to go from here. What the step that you do after this is called partial factoring, where you have to look at a bunch of terms and go, ooh, I can factor something out of these two, and I can factor something out of those two. That's actually a really important skill later on in calculus, where you only factor parts of polynomial expressions. Okay, so that's what the top is, and then I'll just finish the top while I'm at it. I'm going to factor 2d out of the first two things, and I'm going to factor 5 out of the second two things. And that's going to then be equal to d minus 3 times 2d plus 5. And let's make that d look a little nicer. There we go. Okay, so there's the numerator. Let's work on the denominator now. 4 times 3 is 12. What two numbers times to make 12 and add to make negative 13? Negative 1 and negative 12. So this is 4d squared minus 1d minus 12d plus 3. Partially factoring, I can factor a d out of the first two things, giving me 4d minus 1. I can factor a negative 3 out of the next two things, giving me 4d minus 1. And then that's going to give me a factored expression on the denominator of 4d minus 1 times d minus 3. And there's the simplification. This thing here is equal to 2d plus 5 over 4d minus 1, as long as we avoid what values? Where do I get to the point where I'm looking for my values? I go to here, go to the factored version. So on this step here, if d was 3, we'd have a 0. And if d was a quarter, we'd have a 0. Everybody get how I'm getting a quarter? Take 4d minus 1 and make it 0. How do you solve for d? D would equal 1 quarter. Okay, so that's my solution. All right. Then the next page is for you to practice exactly what we just did. And for this chapter, every single lesson has some practice pages like this. And as far as I'm concerned, if you can do everything on the practice pages, you've got this. You probably don't need to do more practice. But if you need more practice, there's also textbook assignments at the bottom of every lesson. So for this unit, I'm going to say that the textbook questions are the optional ones. The ones in the booklet are the ones you have to do. Now, the answer key for this is in booklet B. And again, the page numbers got messed up. So you kind of have to look at the title. It's Non-Permissible Values Practice. So let's see. Let's go to the B one, see what I'm saying, what I'm talking about here. So in the other booklet, oh, whoops, go back. In the other booklet, in the Part B booklet, if you skim to the back, it should have an answer key for everything. The other booklet's much longer than this one. And as you can see, we get lots of funky fractional algebra. And there's even a couple of word problems at the end. There we go. So there we go. Page 8, that's okay, right? That is actually page 8 in the A booklet. And then the next one's page 11, right? Which is right. But then after that, I think when we hit 6.2, the B booklet starts numbering the pages at 7 instead of keeping on going. So this won't be the right number, and this won't be the right number. So we're going to have to kind of renumber that. But anyway, today's homework is that and that. That one's numbered properly. Okay, let's stop peeking at the answers. Let's go back to the questions here. So again, your homework today is these two pages here. This one is page 11. Oh, this one's page 8, sorry. And this one's page 11. And if you want more practice, there's loads there that you can practice. But if you're checking your answers and you're getting all these right, you probably don't need a whole lot of more practice. Okay? All right, I'm going to end my video there for the people stuck in the snow. Thanks for watching.